We're going to talk about the dynamic nature of bone. And before we get into remodeling, I just want to go over modeling again. And modeling is the development of bone, and development starts at 6 weeks after fertilization in the embryo. The majority of bones in the body are formed through this process that's called endochondral ossification. What we already know is that bone is first formed through a cartilaginous model, or in other words, there's a model that's roughly shaped like the bone, and in this case it's a long bone, and it's made out of hyaline cartilage. When this cartilage begins the process of endochondral ossification, it has chondrocytes inside it, and the chondrocytes that are near the center of the shaft of this cartilage start to get bigger. When they do that, it reduces the matrix in between the cells into struts. When this happens, the matrix starts to calcify and it starts to shut off the nutrient supply to those chondrocytes. The enlarged chondrocytes will die and then disintegrate, and they'll leave large cavities within the cartilage. The next thing that happens is we look at the perichondrium that surrounds the hyaline cartilage. The perichondrium is a dense, irregular connective tissue that surrounds the shaft of cartilage. The perichondrium has an inner cellular layer to it, and when blood vessels start to grow along the edges of this perichondrium, it stimulates these cells of the perichondrium to convert to osteoblasts. The osteoblasts then begin to build a thin sheath of bone on the diaphysis of the cartilage. Now that the shaft of the cartilage has bone surrounding it, we no longer call the dense connective tissue perichondrium, we now call it periosteum. It's the same dense, irregular connective tissue, but now it surrounds bone instead of cartilage, and so we call it periosteum instead of perichondrium. In the next stage, these blood vessels start to penetrate deep into the cartilage. They invade that central area where the chondrocytes left large cavities. Fibroblasts migrate in with the blood vessels. Fibroblasts can differentiate, and these stem cells differentiate into osteoblasts. Osteoblasts start laying down immature bone inside the cartilage. We call this the primary ossification center. At this point, there's no medullary cavity, we just have the center of the cartilage filled with spongy bone. This process is going to continue towards both ends of the bone as the blood vessels continue to migrate towards the ends of the cartilage. What we can already see in this picture is that there are hyaline cartilage chondrocytes in there that are continuing to proliferate and cause the cartilage to grow longer, and at the same time we see that there are blood vessels that are growing up towards that cartilage, bringing fibroblasts and laying down that immature spongy bone in the center of the cartilage. In the next stage, what we see is now we get the presence of osteoclasts. The osteoclasts start breaking down or dissolving the matrix of that immature spongy bone that was just laid down by the osteoblasts, and it starts creating the medullary cavity. The osteoclast will continue towards both ends of the bone and continue to dissolve the new bone that's laid down, and at the same time the chondrocytes continue to proliferate, causing the hyaline cartilage to keep growing in length. Here we're seeing the medullary cavity that's been created by the osteoclasts. We see the thin sheath of bone that was created by the perichondrial cells. We see the chondrocytes continuing to grow the length of the cartilage. And now at this stage we start to see blood vessels invading the epiphyses. And the blood vessels invading the epiphyses will fill that area with spongy bone. So the fibroblasts that come in will convert to osteoblasts, and the epiphyses of the cartilage will be filled with spongy bone. We don't have osteoclasts breaking down the newly formed spongy bone, so you won't get a cavity within the epiphyses. The only place there is a cavity is in the diaphysis, or the shaft of the bone. These areas are called the secondary ossification centers. They're found in the epiphyses of the bone. Next, we take a look to see what's happening in the epiphyses. We can see that now it's completely filled with spongy bone. Over time, the articular cartilage that surrounds the epiphyses will be reduced to a very thin superficial layer. It will all be converted to a cortex of bone, except for an area near the joint that will remain articular cartilage. It will remain this articular cartilage so that the bone that articulates with this bone will have a smooth surface to articulate with, and it will reduce the wearing down of the bone as the joint moves. We also see this area in here, which is called the epiphyseal cartilage. This is otherwise known as the growth plate. And what we see happening here is that in the diaphysis, osteoblasts are forming new bone, osteoclasts are breaking down this new bone, and at the same time we see in the epiphyseal cartilage that the hyaline cartilage chondrocytes are proliferating, and they're creating more cartilage, making the cartilage longer. And so what happens is, as long as these chondrocytes are working at the same pace or faster than the osteoblasts and osteoclasts coming up behind it, the bone will continue getting longer. But at some point, the osteoblasts will be stimulated to work faster than the chondrocytes' proliferation. So the osteoblasts work faster, eventually they will catch up to that epiphyseal cartilage, and then growth here will stop. Now, the osteoblasts become stimulated during a period called puberty. That's when these osteoblasts get faster, and eventually they catch up to the line of chondrocytes that are trying to lengthen that cartilage in that area, and then growth will stop. This typically occurs in females about 2 years after the start of their menstrual cycle, and in boys it could continue up until they're young adults. Here we see a micrograph of what's happening at the growth plate. We can see those chondrocytes in there. Do you recognize the cells? They are very distinct look. And those chondrocytes are actively proliferating, going through mitosis, and in the process they're lengthening that cartilage. On the other end, we see that osteoblasts are coming up right behind, and they are laying down osteoid. As soon as that osteoid gets calcified, osteoclasts come up right behind the osteoblasts and will disintegrate them and tear them down. So we continue building the medullary cavity, and as long as these hyaline cartilage chondrocytes can proliferate faster than the osteoblasts, there will be growth in the length of the bone. However, as soon as those osteoblasts catch up to those hyaline cartilage chondrocytes, then growth will stop. So what is it that makes those osteoblasts become stimulated to work faster? In puberty, it is hormones. The hormones estrogen in the female stimulate the osteoblasts to work faster, and so they will catch up to the chondrocytes at an earlier age than in the males. The testosterone also works to stimulate the osteoblasts, however not quite as quickly. In young men going through puberty, they might continue growing because it takes a longer time for those osteoblasts to catch up to those chondrocytes, whereas in the female, that process happens rather quickly and about 2 years after the start of their menstrual period. We're able to determine whether the growth plates are closed or not by looking at X-ray. In this X-ray, we can see that the growth plates are open, meaning that those bones still have the ability to lengthen because the chondrocytes are still proliferating and the osteoblasts have not caught up to those chondrocytes yet. In this picture here, we see epiphyseal lines instead of epiphyseal cartilages. Epiphyseal lines mean that this is where the osteoblasts have completely caught up with the chondrocytes and have formed an epiphyseal line, and there will be no more lengthening of those bones. Endochondral ossification has been the process called modeling of bone, in which we take a hyaline cartilage model and we end up with a formed bone. The shape of this bone isn't going to change throughout life. It's always going to stay the same. But throughout life, we have this process that's called remodeling. Remodeling shows us that bone is very dynamic. It's not a dead tissue, and it can be used as a storage of calcium. Osteoclasts can tear down old bone, and osteoblasts can replace that old bone with new bone and become calcified in the process of remodeling. And this happens on a continuous basis. When we need calcium in the tissues or in the blood, then the osteoclast will tear down that bone and release that calcium into the tissues in the blood. When we don't need that calcium, then the osteoblasts will create new bone and package that calcium up into the bone tissue and calcify that bone tissue. Remodeling will replace the matrix, but the bone itself will stay whole and unchanged. The osteoblasts that are forming new bone will create new osteons, and the osteoclasts that are tearing down bone will tear down the osteons. By the time a person is a young adult, almost 1/5 of the skeleton has been replaced in this process called remodeling. There are other things such as hormones and nutritional aspects that affect bone growth as well, and we're going to talk about those briefly. Calcitriol is a hormone that's produced by the kidneys. It is going to cause calcium and phosphate to be absorbed in the digestive tract. Another hormone is the growth hormone. This is secreted by a gland close to the brain called the pituitary gland, and this is going to stimulate osteoblasts. Then we get new bone growth, and so growth hormone is very important in puberty. Thyroxine is a hormone that's secreted from the thyroid gland, and along with growth hormone, this is going to also stimulate osteoblastic activity. Therefore, it's going to stimulate the synthesis of new bone matrix. There's also sex hormones. The ovaries produce estrogens and the testes produce androgens. They also stimulate osteoblast activity. We also have the parathyroid hormone from the parathyroid glands. The parathyroid hormone stimulates osteoclast activity, and by doing that will elevate the calcium ion concentration in the body fluids. Calcitonin is also from the thyroid gland. Calcitonin will inhibit osteoclast activity so that calcium stays stored in the bone. Calcitonin also promotes the kidneys to excrete the calcium. Overall, calcitonin reduces calcium ion concentrations, whereas what we saw with calcitriol was that it would increase calcium concentrations. Let's look at the homeostasis of calcium. Let's say that we had low calcium ion levels in the plasma. So we have low calcium in the blood, basically. The parathyroid gland will respond by secreting a hormone called parathyroid hormone. Parathyroid hormone will do three things. It will stimulate osteoclasts. So remember, osteoclasts will tear down bone and release calcium. It will also stimulate the intestines to start increasing the intestinal absorption. So whatever you eat, more calcium will be reabsorbed into the body. And it also will respond by having the kidneys reabsorb more calcium. So the kidneys, instead of urinating the calcium out, will reabsorb more calcium into the body. The net effect is we get more calcium in the body. The parathyroid gland causes an increase in the amount of calcium in the body. Let's look at this example. Say we are not in homeostasis and we have a high level of calcium in the blood. The thyroid gland is going to respond to this. The thyroid gland responds by secreting a hormone called calcitonin. Calcitonin will cause the osteoclast to become inhibited, so we're not breaking down bone to get calcium into the blood, but instead will stimulate the osteoblasts, which will make new osteoid, which will then become calcified with calcium. So calcium ends up being stored in the bone. In the intestines, calcitonin will decrease the amount of calcium, so any calcium that you have eaten will then stay in the intestines and eventually get excreted out of the body. Calcitonin also causes the kidneys to respond. In the kidneys, instead of reabsorbing calcium, calcium will be excreted out in the form of urine. So net effect, we have calcium being stored in the bone, so it's decreased calcium in the blood. We have calcium being excreted in both the intestines and the kidney, and so the net effect is decrease in calcium levels in the bloodstream. This ends our segment on bone remodeling and modeling.